Here I'm going to talk about the photoelectric effect, which is evidence that light behaves like particles in addition to waves. Now, the first equation that I have, the speed of light, symbolized by the letter c, is equal to wavelength, symbolized by the Greek letter lambda, times frequency, symbolized by the Greek letter nu. It looks kind of like a curvy looking V. These are all wave properties. This is the old way of looking at a wave, and it still works in most applications. Wavelength would be the length of an entire crest and trough of a wave, or if we continue, so it could be this length here, or if we continued the wave on, you could measure the length between two crests or two troughs, and that should be the same wavelength either way. Wavelength has length units, for example, meters. Frequency is how many waves pass by per unit time. Sometimes we call it waves per second or cycles per second, or simply just 1/seconds. If your length is meters and your frequency is 1/seconds, multiplying those together gives you meters per second, distance over time, which is a good speed type unit. Now, the next equation has the energy for a particle of light, or photon. Keep in mind that this is a particle property. We're pretending like it's a bundle of energy. And that particle property has Planck's constant, h, which is just converts the units, and frequency, which is a wave property. So here we're relating wave properties to particle properties. It's got a little bit of both. And now what I want to try to do is discuss how the photoelectric effect is evidence of both particle and wave properties. And the photoelectric effect is the ability of light to eject electrons from a metal. If we think about some chunk of metal, metals conduct electricity, which means they have electrons inside that can move around. That's one way to think of it anyway. So if you shine light on this metal, it might knock out an electron. And not all types of light can knock out electrons. So what types of light can and what types of light cannot? Let's say we look at a sample of red light, and let's say the red light looks something like this. If this red light doesn't knock out electrons, you might think, well, hey, let's make it a little brighter. Brightness or intensity corresponds to amplitude, how high and low the waves go. So if I make it go much higher and much lower, that seems like this wave would really whip the electrons up and whip them down and might be more likely to knock them out. It turns out that that is not the case. And one way to think about this is if we pretend like these are particles, this red light at the top with low intensity might be a few small particles of light. If we make it more intense, we make more particles, but they're still quite small. So these tiny little bundles of light, no individual one can knock the metal out. If a ping pong ball won't knock something over, throwing 10 ping pong balls at it one at a time isn't going to knock it over. Instead, if we take light of higher frequency, like say this blue light has much higher frequency, many more waves will pass by per unit time, this blue light is going to be like light of much bigger particles. Each particle of light has a lot more energy. So these big honkin' particles can knock out the electron from the metal, whereas the little tiny particles won't be able to. If we go back to what would this look like if it were brighter, it would have higher amplitude but still really high frequency, and this would again be like more big particles. And it turns out that if you increase the brightness of this blue one, it just knocks out more electrons, as though more and more big honking particles are knocking electrons out. So if light was a wave, it would depend on amplitude. And the answer is does not depend on amplitude. The ability, so light is not behaving like waves in this case. Instead, it depends, the ability of light to eject electrons from a metal depends on frequency. And you might remember from the equation E equals h nu, where nu is frequency, larger frequency means larger energy. So if light, the ability to knock electrons from metal depends on frequency, it depends on the energy of each particle. So tiny little particles, low frequency, low energy, do not knock out electrons. But big particles, high energy, high frequency, do knock out electrons. That's evidence that light behaves like particles.